Okay. Okay. Yeah. First of all, thank you for having me here today. As already mentioned, I will be talking about most recent work, and I just noticed that I put the wrong title on the slides. But this is basically work that I published at the ICLR conference in Singapore, roughly two months ago, something like that. And I will be talking a bit more in detail about this. And there are some small extensions as well that have not yet been published on this method that I will also be discussing. Now, to be clear, this method is called Twin Network Augmentation. And the main idea behind this method was that it was inspired by contrastive learning. So don't know how familiar you are with contrastive learning, but basically the idea, at least for the method that it's most inspired by, is that you want to take different views of the same sample and then align those views such that basically the outputs for a neural network for the same for different views of the same sample are similar, and the outputs for different views of different samples are dissimilar. And this method is SimCLR. And typically, how you get those different views of the same sample is by using augmentation. So you use things like cropping, random color jitter, and more to get two different representations of the same image, which you then feed to the same network. So this is a very simple illustration of this. So you have a dog, and then, for example, you take two different augmentations of that, you feed it to the same network, and afterwards you feed it through an additional linear head. And then you want the outputs, so the logits, to be similar for the same views of the different views of the same sample, and different between a different sample, for example, a chair. Now, we thought in this case you use augmentations, but there's also an idea that trained networks, they can also provide views, or partially trained networks can also provide views of the sample. And the idea behind it is that different networks, they contain different features, but they will have roughly the same outputs. So the logits might differ slightly between different networks when they are trained, but they have a different way of looking at the input. So if we use those as different views and we align the outputs, then we might also be able to improve the accuracy in this case, because we use image classification in the paper, but maybe also other loss-based things. And to first validate whether actually different networks have different features, we use a technique called centered kernel alignment. And this technique, basically, it is a way to, given a set of inputs, you generate features for a certain layer in the network, and then you calculate some kind of similarity metric on the features between two different networks, their layers. And so when we do it for two randomly initialized networks, we can see that the CKA, so the similarity, is pretty high. We get around 80 to 90% similarity in each layer. So those are still quite similar. But if we go to a 5% trained network, so this is after, in our case, this was after 10 epochs of training, then we can see already that some layers, the features, they start to be much different when between two differently trained networks. Going further, we can see that indeed, while in some layers there is a large overlap of features, large similarity, in some layers there's also very little similarity, only around 50%. So the different networks, they do contain different features, so we could be using them for different views of the same sample. And we only want to match the outputs of those networks. So we keep the internal features separate because we want our models to evolve separately as well. We want to have the same output, but we don't want to give too strong constraints on how our models should evolve, because we hypothesized that if you give them less constraints, then they're more free to evolve, and likely they will get better outputs. They will get better results at the end. Now, the method itself starts quite simple, and it starts by initializing two networks. In the paper itself, we used two networks of the same architecture. So for example, if we use the Resonant 18, then we used two Resonant 18 models, but differently initialized. Hypothetically, and we also did some ablations on that, you can use two different kinds of networks. So later in the talk, I will be giving an example of using a vision transformer and a Resonant 18 model. And the main constraint is only that the outputs are the same format. So if you have logits for a classification problem, let's say, then if one network only classifies 10 classes, the other network should also classify 10 classes, because otherwise you can't match those logits. Additionally, we with initialization, we did a brief test to see how different those networks need to be at initialization. And we found out that if you just randomly initialize one layer and keep the other layers exactly the same weights, or even a couple of parameters, because there is so large parameter space in those networks, even the very small variations allow for successful run of our algorithm. So there can be very little difference between the networks at initialization, and still we can see correct application. We can see, in our case for the classification problem, we can see an accuracy increase. The next step is we introduce an additional loss term, and which matches the logits. And we also optimize still for the original problem. So in our case, we use image classification, which uses a cross entropy loss. So for each network, we optimize the cross entropy loss. And we also have an additional logit matching loss, which just is the L2 norm on the output logits. And finally, we also have an alpha, which is the parameter that determines the influence of this logit matching loss in the total loss. And this is basically to make sure that it does not dominate the other losses, because if the logits are if there are a lot of classes, for example, this L2 distance can become quite large as well. And that's basically how the methodology works. And at the end, you can discard one network. So this means that during training, you have double the training cost because you train two networks in parallel. But at the end, you only have the inference cost of training a single network. And typically, what I would suggest, of course, is to discard the worst network. But in the paper itself, we just discarded a random network to make it less seen that we cherry-picked results. Now, there is a method that is quite similar to this approach, and this is called deep mutual learning. The main differences between our method and deep mutual learning is that rather than matching the logits directly via the L2 norm, they instead convert the logits first to probabilities using the sigmoid, using the softmax function, and they use KL divergence on the probabilities rather than matching the logits directly. Now, we believe that our method is superior, and we also have empirical evidence for that in at least the use case that we considered. And the reason why is because softmax is a function that squashes the logits. So the idea behind the softmax is that you convert to probabilities, and a probability is sum to 1, for instance. So this means that, and it's also between 0 and 1. So there a lot of information is lost, and due to this exponential, also differences that are within the logits, so within the logit, are either exaggerated or diminished. And also negative information from the logits is lost because you go from a real valued to a 0 to 1 set. So there's like a lot of information loss. And also, final reason why we think it's better is because there's also a recent work for knowledge distillation, which uses logits and the L2 norm. And they also find that for knowledge distillation, in that case, logits function slightly better than using probabilities. And they also have theoretical analysis on why exactly, but if you are interested in that, I would suggest to read that paper as well. Now, for our experimental protocol, because we use computer vision as the main task and image classification more specifically, our datasets are, of course, image datasets. So ranging from least complex to most complex datasets, we use CIFAR10, which is a 32 by 32 images of 10 different classes. Then CIFAR100, which follows roughly the same format, but rather than 10 classes, it has 100 classes. Then TinyImageNet, which is a downscaled dataset that is a subset of ImageNet. So it has 200 classes and 64 by 64 images. And then finally, ImageNet itself, which is probably the most well-known dataset from this set, which is 1,000 classes. And when the images, they are actually unbounded, but when processed, they are often rescaled to 224 times 224. For the networks, then, in that case, we also have more and less complex networks. The least complex is a simple convnet of, I think, 3 layers, which we mainly use for the easier data sets. Then we have a mobile net, which is a network that is actually optimized for portability. So it has very little parameters, but it's quite efficient in how it works. Then we have residual nets, which have been a major innovation 10 years ago or something like that. And finally, we have a vision transformer, which is one of the more recent innovations. Then empirical, comparing our approach to deep neural learning. As mentioned, we believe it's superior, but we also have solid evidence, at least in the settings that we tested, that we actually do outperform this methodology. So we can see, for example, here in these 2 columns, that our approach gets better validation accuracy than deep neural learning. So at least in our use case for convolutional neural networks and image classification, it's better. What we also see is that for deep neural learning, there is this dependency on the learning rate, because if we use a higher learning rate, then the deep neural learning solution fails to converge or gets very bad results. That's also why we have this trade-off parameter alpha within our definition, where we can re-rate this loss term compared to the other losses, because for deep neural learning, this is not present in the definition, and as such, if you just naively apply the method as it's defined, then you can get issues with non-convergence. Comparing then our results against the single training of a network. So if you just train a network normally compared to our approach, on the different computer vision benchmarks, we can get consistent performance gains. So in every benchmark that we tested, in this case, it's roughly going from least complex to most complex, we can see better validation accuracy, which is, of course, a bit to be expected as well, because during training, you have those initial trainable parameters from the Twin network, and you have this additional guidance. So we would expect a gain in accuracy. Now, on the most easy case for the CIFAR10 datasets, we can see a limited gain of less than 1%. This is also quite to be expected, because in those cases, the networks, they already get a very good validation accuracy on these settings. So they already are quite good. Also, for the convnets, we similarly see only limited gain. This is also to be expected, because these are quite tiny models, and they as such don't have a lot of representation capacity, and as such there is likely also less to be made of gains. Now, for the other cases, we can see better results. We can see results in gain ranging from 1 to 5% validation accuracy increase, which is quite significant. Now, continuing to this loss term analysis. So what we do here is we want to see, actually, when you just train 2 networks separately, when you don't enforce this additional logit matching loss term, what would happen to this definition? Would the networks just converge to the same output, to the same logits every time, depending on a random seed, or not? And what we can clearly see is that no, there is a significant difference at the end. And for Resonant 18 CIFAR100, there is some convergence back to a similar logit between the 2 different networks, while for Resonant 18 and TinyImageNet, this is not the case. So and more generally, we can see a steady increase in the distance between the logits, and then followed by a flattening phase in the case of present 18 tiny ImageNet, or even flattering phase for CIFAR 100. Now, if we do apply this logit matching loss term, we can see a different result. We can see that, as expected, because we match those logits together, we put additional constraints on how the network is trained, that their distance is much closer, that they stay much more similar, the networks, but importantly, they do not get exactly the same outputs, which is likely also almost impossible because there is a very large parameter space. So unless we maybe fully force this, they still get similar, they still get slight different representations at the end. And as mentioned, no significant increase. So we want to compare against methods that also are quite similar. So methods that do have an additional computational cost during training, or maybe also during inference, and do a comparison with that. Because comparison with a single train network, so a standard train, it's valid, but it's also there is less computational requirements. So the first comparison we did is with knowledge distillation, in which basically there is a teacher network, which is pre-trained, and a student network, which will be trained to mimic the teacher network. Now, let's assume that this teacher network already exists, so that the training cost for the teacher network is non-existent because you have it somewhere, and that training cost of the forward pass is roughly half of the training costs in total. So then we could say that knowledge distillation has roughly 1.5 times the training cost of training a network normally. And because at the end we only use a student network, the inference cost is the same as using a single network. Now, for our comparisons, we used a student network and and a teacher network that were exactly the same architecture, just as in our method. But typically, you would of course use a teacher network that is better, that is higher representational capacity than student network. If we compare then our approach to the knowledge distillation approach, we can see that the original knowledge distillation by Hinton et al., which matches the KL divergence on the probabilities, gets slightly better than the standard approach, than just training a network normally. Likely because also in this case, only the teacher and the student model, they have a similar representation capacity. If we would use like a stronger teacher model than the student model, we would see better gains, but that would be less comparable to our setting. And then the knowledge distillation by Kim et al., which uses the logits and the and matches with the L2 norm, it gets better results, which they also mentioned in their paper. And then we can see that our method gets even better results than those. And likely the reason why our method is even better is because in our case, both models are allowed to evolve. And with knowledge distillation, at some point, your student will be better or almost better than the teacher. And at that point, there's not really any knowledge left to be extracted from the teacher. In the case for the logits, you can see that there is still some additional gain because your teacher is slightly different than your student. So there is some additional representations that are there. But in our case, we allow both models to evolve together, and they get better from each other. So there is more to gain. A second comparison that we do is with model ensembling. Now, model ensembling is very simple. You train two networks separately, and then you average the outputs of both networks. And this is also one of the ideas behind this is that, a network that is trained is slightly different than the other network that's trained. So if you can combine the different views, you get better results. And in this case, very straightforward, double the training cost and double the inference cost because you have two networks that you use both during training and testing. And in that case, we can see two interesting things. The first thing is if we take a look at this, this blue line here, so ensembled through blue line, this is just two networks that are ensembled and separately trained. We can see that our method, still this orange line with false, still is better. But also the networks that we use with Twin Network Augmentation, also with deep mutual learning, they can also be used for ensembling. And they can, if you combine them like that, you can get even better gains. Now, the disadvantage of combining them with ensembling is that you lose the single network inference cost, so you have double the inference cost, but showing that you can still use ensembling on these methods as well to, if necessary, increase the validation accuracy even more. A third approach that we studied was using wider networks. So this is also very straightforward. What happens there is the number of channels in each layer of your network is just multiplied by a fixed multiplier. So in the case that we studied, double or quadruple. And in those cases also, because you have more trainable parameters, the training cost and the inference cost is also doubled or quadrupled. And we can see in this case, we are this with Twin Network Augmentation, that Twin Network Augmentation with two normal width networks outperforms the double and quadruple width networks as well. So showing that it's not just a case of throwing additional parameters to the network, but also like the competition between both networks to improve each other. And then we can ask ourselves the question, do we actually need to enable this logit matching loss throughout training or not? And what we can see here in these graphs is that almost from the start of training, that the orange line, which is Twin Network Augmentation, is better than the blue line, which is the standard training. So this might indicate that indeed it is necessary to train and to enable this loss all the way throughout training. However, when we do an ablation where we enable the loss term later, so this to the left is after 25% of training, in the middle is after 50% of training, and at the right is after 75% of training, we can see in each of these graphs a pronounced spike at the moment where we enable this loss term, showing that it might also be possible to enable this loss term later and only profit from it in the last few epochs of training. However, it's barely noticeable, but enabling it from the start is still a little bit better. And also because during training, you basically need two networks of roughly the same power, the same predictive power. It's best to just use those two networks to use the matching loss all the way throughout training. Then, as mentioned before, in our previous experiments, we all used the same architecture for both networks. Now, in this case, we wanted to see what would happen if you use different networks. So if your Twin network and your base network are different, so we have two settings. And the first one, we use different ResNet models. So don't know how much you know of ResNet models, but basically in ResNet models, there are different definitions of them and the number behind. So there's ResNet 18, 34, 50, and I think also 101. And those are indicators of how deep they are, how many layers they have. And from our experiments and also from logic, you can see that deeper models, they get better accuracy in those cases when trained. So we thought maybe we can increase the validation accuracy of a ResNet 18 model even more when we use it together with a ResNet 50 model for Twin Network Augmentation rather than using two ResNet 18 models, because the ResNet 50 model has better representational capacity, so it will maybe aid. And actually, what we can see is that is not the case, that using the larger model has a negative impact on the ResNet 18 accuracy. So initially during training, the ResNet 18 model is better. So if we would stop training right here, the ResNet 18 model with the ResNet 50 together is better. But we can see a stagnation at some point where the other models, the smaller models, overtake the ResNet 18 model with the ResNet 50 model. And the reason why we think that this is happening is because those models are too dissimilar. So the matching loss that we currently have, it's bidirectional, so it just minimizes the distance between the two logits, but this also means that it can, if one network is better trained than the other network, it can pull up the worst trained network, but it can also pull down the better trained network. And we see some differences in how the training process of ResNet 50 differs from ResNet 18. So for example, here in this curve, the ResNet 50 is converging slower than the ResNet 18. So we hypothesize that this is likely due to that. The second case is with a vision transformer. And vision transformers, they are somewhat notoriously to train on small data sets. So typically, if you would use a vision transformer for a data set with limited samples, what would happen is you choose a vision transformer that is pre-trained on a very large data set. I think currently there are data sets with millions of images on which they are pre-trained. And then you just fine-tune your vision transformer on that small data set. And we did an experiment training a vision transformer from scratch on tiny images. And indeed, we can see, compared to training a ResNet 18 from scratch, we have almost 20% accuracy loss. Now, you might say this is maybe something to do with different parameter counts, but the vision transformer, while it has slightly less parameters than the ResNet 18 model, is not enough. Yeah, the difference is not that significant to warrant this 20% accuracy drop. And the main reason why the vision transformers actually are hard to train on small data sets is that they have less inductive biases than the ResNet 18 model. Now, first, what we wanted to see is if we just use two vision transformers with Twin Network Augmentation, do our results differ significantly or not? And then we can see already an increase of, I would say, 4 or 5%, which is roughly similar to the increase that we saw for using two different ResNet 18 models. So this is roughly in line with our expectations. But then we thought we could also increase it even more by using a ResNet 18 model rather than a vision transformer, because the ResNet 18 model gets better validation accuracy. And indeed, if we do that, we can see an increase compared to training a single vision transformer of roughly 10%. So while we cannot yet match the validation accuracy of training a single ResNet 18 from scratch, we get significantly better results than just training a vision transformer from scratch. And then some of the extensions. So these are currently work in progress. So this is not yet published. And those are mainly focused on two things. First, constraint matching. So as already mentioned, our matching currently it's just bidirectional. So you just minimize the distance, but there's no real notion of which model should actually follow which model, and also using multiple twins, because our current definition allows for only two networks, but maybe using 3 or 4 networks would be better even. Now, we call this loss function for the constraint matching, and indeed it's bidirectional. So you minimize the distance between both, but that will mean that likely both logits are pulled in the same way to each other. But instead, you could also maybe match the one logit only to the other. So push the logit for network B closer to network A, but not pull the logit from network A closer to network B. So there are some ideas that we are currently exploring to limit contradictory information. And this is, for example, weighting the logits in the batch. So seeing, for example, to the cross entropy loss and see whether if one network has a lower cross entropy loss, whether we then should pull more to that network, or if it's a higher cross entropy loss, we should pull less to that network. And the other is to maybe disable certain logits once logits for a certain sample once that sample has been correctly classified. Once again, very much work in progress, so we don't have any results yet for that, but this is one of the approaches that we're currently testing to see whether and exploring to see whether we can improve even more the validation accuracy. And the second is using multiple twin networks. So in that case, what we notice is that using this approach is in essence equivalent to matching each logit to the mean logit, so the mean of both logits. And this is how that would be then worked out. And okay, there is an additional factor 2 here with the alpha if you work it out, but we can just fold that in back in the alpha parameter and then just for simplicity use it like that. And we can restructure this as follows and extend it to n networks by, for each network, so in this case network I, we have this additional loss term where we have, in our case, the cos entropy loss, but we could also use another task specific loss, and we match the logit to the mean logit. And for those, we do have some results, but basically what we notice there is that there are diminishing returns when you use more than one, when you use more than two networks. So for a single network and two networks, we get a quite big jump. For two networks to three networks, there is a smaller jump. And for 3 to 4 networks, there is no significant increase or decrease. So unless performance is really critical, I would suggest to maybe use two networks. And yeah, that was our paper and some additional extensions that we are currently exploring. I want to thank also Lucas and Jose for their collaboration and getting this project done. And if you have any other questions that we will not be discussing in the discussion, you can also contact us via email.